Newton and Lagrange polynomials do not provide a convenient polynomial of the form of this. So they have basically their own forms. Newton has the finite differences. Lagrange has the Lagrange terms. But we can also use some interpolation polynomials in different versions. So this is a different version you can see here. X has an increase of the order in the function. So if we want to fit this to a data, then we need an additional operation or additional solution of the interpolation, let's say. So to determine n+1 coefficients, at least n+1 data points are required for such a different polynomial form. This is different from Lagrange and Newton. And therefore, some simultaneous linear algebraic equations can be used to calculate the A's. Simply, for example, let's say we have a parabola with with 3 terms. We need then 3 coefficients. So this is second order, 3 coefficients and 3 data we need. And these are the data, let's say. And for each of these data, we can simply write these down here. So x0 and fx0 like this, and x1 and fx1, x2 and fx2, as you can see here. So now we can use this by an elimination method. So we have 3 data or 3 functions and 3 data. And we have 3 unknowns. The unknowns are a0, a1, and a2. So we can solve this by Gauss elimination, for instance, or Cramer's rule, and get the a0, a1, and a2. Equation system is usually ill-conditioned. So this kind of systems are ill-conditioned. So that's why the resulting coefficients can be highly inaccurate, particularly for large n's. So if we increase the terms, we can have some issues in solving. If you must determine an equation of this form, limit yourself to lower order polynomials and check your results carefully. Usually, Newton and Lagrange polynomials are good enough. But if you prefer such a different polynomial fit for the interpolation, be careful on that and try to use some lower orders like the parabola with 3 terms or 4 terms, etc. We can also need to use the interpolation in an inverse order, and it's called inverse interpolation. And for that, let's check the interpolation first. As an example, usually have the inputs of a data in a uniformly spaced way. So you can see here, for example, inputs are 1, 2, 3, 4, 5, 6, and 7. So we have uniform space of 1. It doesn't have to be like this, but usually it is like this, we can say. And the outputs are obtained from 1 divided by x as these values. Now suppose that we have fx values. We don't know this, and we have these values only, and we want to find x, this data, or a value from this. So in the regular interpolation, we want to find fx for a known x. So let's say for 2, we want to find 0.5. We don't know 0.5, but now we are reverse the process. We know 0.5 and we want to find 2, for example, using the interpolation. And here, let's say fx is 0.3, and we want to find x for it. So we know that we want the x value of 0.3, or actually somewhere here. So this problem is called inverse interpolation. And if we know the function, we can check the true value. The true value is 3.333. It's somewhere here. How can we do this? Let's see that. But now we don't have the uniformly spaced inputs. So the inputs becomes actually reversed. So we took the fx's to the top like this, and these are not uniformly spaced, as you can see. And the outputs are uniformly spaced now. Non-uniform spacing of inputs may lead to oscillations in the interpolating polynomial. So as we said, we don't need to have uniformly spaced data, but if it is not uniformly spaced, then there can be oscillations, there can be some issues. And therefore it's preferred to have uniform order. And in the inverse now we don't have uniformly spaced order. That's why we want to have an alternative strategy, which is to use the original data to fit interpolation. So let's use this first to fit an interpolation, just regular interpolation. the inputs are x's and outputs are fx's, and we want to find unknown x's, which makes the interpolating polynomial results equal to the given fx's. And this way, the inverse interpolation is actually a root finding problem for the fitted polynomial. Because we fit the polynomial to the same input and outputs, but we want to find the x value for fx, it becomes a root finding. We can show this in an example. In this slide, we have an example for the inverse interpolation. Let's say we have 3 data, and inputs are fx's and outputs are these values. So, but now assume that we don't know that the data is coming from fx is the 1 divided by x. And we want to have an interpolation polynomial which predicts x values actually. And we want to predict the output fx equals 0.3. So 0.3 is somewhere here. We want to predict the x value for that. Let's solve this problem now. Initially, we are going to use an interpolation function. We simply use the quadratic function with 3 points, because actually with 3 constants, let's say, because we have 3 data. And maximum we can use this quadratic. We can use also linear, but because we have 3 data, why not we are using the quadratic function. Let's substitute each of 3 data into function with regular x and fx's. So x's are here, fx's are here, and have this data like this by adding these here. So solve these, apply Gauss elimination to solve, and f2x's x function becomes like this. These a0, a1, and a2, we find these from Gauss elimination as 108, 0.3, and 0.404. And if we want to find the value of 0.3, now 0.3 is fx value. We write here 0.3, and we want to find this x. But now this is kind of a root finding problem because x is not isolated here. You need to try an isolation of x, and you can use root finding. You can apply root finding formulas, numerical formulas if you want to, like the Newton's method or bisection algorithm, for instance. But instead, because this is just a second order polynomial, we can use the analytical root finding of this. This is basically b, which is this abc, and b squared 4 times a times 4 times c times this value, and 2 times c when we say ABC. And these are 2 results that we obtain because it's a second order. We will have 2 x values, and from here we need to think which one gives a better value actually. Which means that if we check the trend of the data, basically 0.3 is in between fx is 0.3. 0.3 is somewhere here. It should be similar to 3 actually. Then it should be this one. It cannot go very high like this. So this looks like a good estimation, this one, according to the trend of the data. And you can use the inverse interpolation in this way, simply a root finding formula. In the previous slides, we mentioned about the equalist space data, so let's talk about it a little bit. And we said earlier that also the Newton and Lagrange polynomials are compatible with arbitrarily spaced data anyway. But before the advent of digital computers, these techniques had great utility for interpolation from tables with equalist spaced arguments. So usually it was preferred to have an equalist spaced data. So for example, this example is from the previous slides as well, for a different polynomial interpolation than the Newton's and Lagrange we mentioned before. And here we are talking about Newton and Lagrange now, and it's usually used with arbitrarily spaced data. However, now there is no need for equalist spaced data because the formulas are subset of computer compatible Newton and Lagrange schemes, so because we are able to use computers, it is easy to use them for arbitrarily spaced data as well. And many tabular functions are available as LaSalle library subroutines. So Newton and Lagrange is good for arbitrarily or equal space data, any of them. But the function that we mentioned in the previous slides, the function with increasing orders, because we are solving a linear set of equations using Gaussian elimination, having an arbitrarily spaced data can be a problem in that scenario. That's why it's more preferred in that type of polynomial, if we are using that in interpolation, preferred to have an equal space data. But in Newton and Lagrange, we don't need to them. We can have arbitrarily spaced data for this as well. So still equal space data is needed in particular to derive numerical integration formulas. So if possible, have equal space data. And hence interpolation with equal space data is needed for the numerical integration formulas for the solution of ordinary differential equations in the following chapters. So we prefer equal space data for numerical integration and the numerical solutions for differential equations. And let's talk about extrapolation as well, because we are actually using a data to have the function value of a x value in between the data. Now we can still use this interpolation function to predict a value of data which is outside the initial data. So let's show it here. We, for example, have this black curve as our actual function, but we know only x0, x1, and x2 from the black curve, and we apply a polynomial here, a parabola for instance, or a quadratic Lagrange or Newton's polynomial, let's say. This is the function, and you can see that it doesn't predict the rest of the curve in a good way. It just goes down like this. That's why when we want to predict, for example, the value of this, it's very small, in negatives almost. It goes down. So extrapolation should be can be done, but we have to be careful because because it's not using a data around here. It's not able to predict this well. And the most accurate interpolation is obtained when the unknown lies near the center of the base points. So basically, if we know the data and have a point in between, it's the most accurate one. And this is violated when the unknown is outside the range. If the unknown is somewhere here, so we are not able to get an accurate result, it says. Hence, the error in extrapolation can be very large. And the open-ended nature of extrapolation, this is open-ended, represents a step into the unknown because the process extends the curve beyond the known region. So it represents the region you can see here, which is beyond the known region. Known region is here. As such, the true curve could easily diverge from the prediction. As you can see here, it's diverging too much. Extreme care should therefore be exercised whenever a case arises where one must extrapolate. If you need extrapolation, just be careful. It's not recommended, but if you need to, be careful. We finished chapter 16 here, and we talked about the Lagrange interpolation polynomials here. And in your book, it is actually in chapter 18, sections 18.2. And also, we talked about 18.3 to 18.5 in your book, and these were about the additional polynomial form for interpolation, which is different from the Lagrange and Newton's. We mentioned them already, and we are using a set of linear equations to fit that function type, and using a root finding problem if we have an inverse interpolation for that. You can go back to your book or to these slides in here to remember the Lagrange interpolation. Thank you very much for listening. See you in other classes.